Chapter 10 is about thermal properties of matter. Here we are going to discuss about thermal expansion. What is thermal expansion? When a substance is heated, it expands. It means it gets bigger. When it is cooled, it contracts, gets smaller. This happens in solid, liquid, and gases. Now, particle view. When heated, particles move, vibrate faster. They hit each other harder and move further apart. The gap between particles increases. Important point here is particles do not get bigger, only the spacing increases. Which expands the most at constant pressure? So solid expand least, liquid expand more than solids, and gases expand the most. Uses of thermal expansion. Liquid thermometer. Liquid, example mercury, alcohol, expand when heated. Level rises up, the tube. Bimetallic strip. Two metals that expand are different rates. Used in thermostats, automatic switches. When heated, one side expand more. Strip bands can make or break a circuit. Problems: railway tracks, bridges, roads. Metal or concrete expand in hot weather, can buckle or crack. So engineers leave expansion gaps. Let's talk about specific heat capacity. Internal energy of a system equals to the total energy stored in the system particles due to their motion, which is kinetic, plus the position, which is potential. So when you heat a substance, particles move faster, kinetic energy increases, internal energy also increases. Temperature is linked to the average kinetic energy of the particles. Higher temperature, particles move faster on average. Heating a system can increase temperature or cause a change of state. Example: melting, boiling. A specific heat capacity, which is represented by a symbol C. The definition is the energy needed to raise the temperature of 1 kilogram of a substance by 1 degree centigrade. Its unit is joule per kilogram times degree centigrade. Interpretation: high C, example water, needs lots of energy to warm up, cools down slowly. The reason is that the water has high specific heat capacity. Lower C means lower specific heat capacity. Example: metals like aluminium heats up quickly and cools down also quickly. Our formula E is delta E equals to mc delta angle, where delta E is change in thermal energy in joules, m is the mass in kilograms, C is specific heat capacity joule per kilogram times centigrade, and delta theta is change in temperature, delta which is degree centigrade. Now, investigating specific heat capacity. Aim: to measure the specific heat capacity of a solid block, example aluminium, using electrical heating. Basic setup: you will need metal block with holes for heater, thermometer, power supply, ammeter for current 1, voltmeter for voltage V, stopwatch, insulation around the block. Method: place heater and thermometer in the block. Measure initial temperature. Switch on power, start stopwatch. Keep voltage and current constant. Record V and I and temperature rise over a fixed time. Example: 10 minutes. Switch off, record final temperature. Here the energy supplied by heater use the equation E equals to I times V times T, where E is energy supplied in joules, I is current ampere, V is voltage V, and T is time in second. This is the input energy to block minus any losses. We assume energy supplied is equal to increase in thermal energy of block. So our equation will become delta E equals to mc delta T. Rearrange to find C, so we can get C equals to delta E over m delta T, where m is the mass of the block and delta T is the temperature rise. Sources of error and improvements. Heat loss to surroundings makes C too high. Use insulation around block. Use a lid if using water. Poor thermometer reading. Read at eye level. Avoid parallax. Electrical reading. Take several readings of voltage and current. Use average. Better use a joule meter to measure energy directly. Safety. Heater and block gets very hot. Don't touch metal directly. Keep water away from electrical equipment. Allow equipment to cool before packing away. Let's talk about melting and boiling now. They have fixed point in water. Melting point of ice is 0 degrees centigrade. Boiling point of water is 100 degrees centigrade at normal atmospheric pressure. These are called fixed points. Melting and boiling and temperature. When a pure substance is changing state, melting or boiling can occur. Temperature stays constant even though energy is being added. Energy goes into breaking intermolecular forces, not increasing kinetic energy. Boiling liquid to gas. When heating liquid water, temperature rises until 100 degrees centigrade, then stays constant while boiling. Extra energy used to overcome intermolecular forces. Liquid become gases in the form of steam. Then we have reverse process, which is condensation. Here gas turns to liquid when energy is lost. Now let's talk about melting, which is from solid state to liquid state. For ice, temperature rises to 0 degrees centigrade, then stays constant while melting. Extra energy used to break forces holding particles in fixed position. Reverse process, freezing, which is liquid to solid again. Alright, now let's discuss heating and cooling curves. So, flat horizontal section of a curve shows change of state, melting, boiling, freezing, condensing. Temperature constant, energy used to change state. The sloped section of the heating curve shows single state, solid only, liquid only, gas only. Temperature increases or decreases with energy. Now let's discuss evaporation. What is evaporation? Evaporation is the change of state from liquid to gas at the surface of the liquid and at any temperature. It happens below boiling point. Only surface particles escape. Now, cooling by evaporation in a liquid, particles have range of energies. Some near the surface have high enough energy to escape. These high energy particles leave. Average energy of remaining particles decreases. Lower average energy leads to temperature of liquid falls and then it ultimately cools down. This is why sweat cools your skin. Alcohol wipes feel cold. Factors that affect rate of evaporation. Number 1, temperature. Higher temperature means particles have more kinetic energy, more can escape, and there will be faster evaporation. For surface area, larger surface area, more particle at surface, more can escape, and there will be faster evaporation. Then air movement like wind, fan, moving air removes vapor above liquid, keeps air unsaturated, more liquid can evaporate, and there will be faster evaporation. Let's talk about evaporation versus boiling. Evaporation happens at any temperature, only at the surface. Slow process, no bubbles throughout the liquid. Then we have boiling, happens only at boiling point, occurs throughout the liquid, bubbles form everywhere, and fast process. With this, we have finished our this chapter. See you in our next chapter.